Okay, so now we are on the analysis. That looks like a good spot as any. Okay, so it's a good spot as any to talk about the analysis of the MG lab. Calculate heat of formation for MG for each trial and determine its average. So, what we're doing is we're using the idea that delta H is equal to Q, a constant pressure. You guys are very good at finding Q for the calorimeter. What you're going to do is you're going to find, use Q equals MCAT. You need the mass of your HCl, specific heat capacity of either HCl or water, and change of temperature. And it says to do that for each trial and determine the average. So to find the average, you'd add up the Q energies and divide by 3. I think you guys got that. For every situation, energy is going to be absorbed. So the value will be positive. And what we're assuming is that the energy leaving the reaction will be entering the calorimeter, and that no heat will be lost to the surroundings. So any energy absorbed, any Q value absorbed by the water, is going to be equal to the delta H given off for the reaction. And now, I think that that's not a problem. It says, what is the system in this experiment? Okay, is that the cup? Is it the water? Is it the air molecules? Is it the metal? And you should be able to define that knowing what a system is and the surroundings, whether or not the system was isolated or closed or open. And then it says, do you determine the enthalpy of formation of Mg directly or indirectly? Explain. Did we find the energy consumed in, or the energy changed from magnesium to Mg2 plus by measuring the energy stored in those molecules? You guys, I hopefully can talk about that. Compare the potential energy of the magnesium strip to that of the magnesium ions. So if we're just going to, you could easily do number 3 with a graph. You could say if this is potential energy increasing on the y-axis, and you could say Mg, and you could say Mg2 plus. And you should definitely be able to say if it goes up or down. With all the evidence you have, what you felt, etc. You could talk about it quantitatively. Like I think I saw in Alex's notebook, he was ready to go with some kind of graph. I think he had time on there, which is cool. There's a more advanced level of stuff that we could do with more chemicals and graphing temperature over time and talking about that, but that's not the purpose of this lab. That's different, would be a different lab. But should be able to talk about the potential energy involved, and you would definitely need some units here if you do it that way. You should be able to tell me the units for energy. Okay, look up and cite your chemistry source, theoretical value of heat of formation of Mg, determine your percent error. think this is where it's hard. Think this is where you're like, oh my God. Okay, first of all, we just got all of our information for our pre-lab out of our book. Why don't we just sit there? Why don't we just sit there and move from there? Use your source as the book if you're going to use the book, and we're going to do number 4. How are we going to relate Q experimental to our enthalpy change experimental to our calculated values? You have to know how to calculate the values. So let's look at our pre-lab. Okay, so here we go. We could set it up like Hess's law, or we could set it up as a direct method. I'm going to set it up like Hess's law, because if you look at our net ionic equation, which I'm going to show you right here, MgS plus 2H plus AQ going to Mg2 plus AQ. And if you're like, Miss Pappas, we didn't learn net ionic equations. If you just used a regular equation, you could use this one just as well. You would just have to have the foresight to see that Cl is minus here, and it's Cl minus as well. It's just easier to see as a net ionic equation that Cl2 minus has undergone no chemical reaction of any kind. It is what it is, and it was what it was, and there's no change. So here we go. I'm just going to leave it out, but if you included it, it would just be 0. So I'm just going to leave it out though. And we have, NH2 gas. So let's just use Hess's law. Let's just find MgS in our reactions that we looked up in the book. And there's MgS. It's written on our reactant side. There it is. There it is. There it is. So we're going to leave it just as is. We have 1 mole of it, so we don't need to multiply our delta H values by anything. I'm just going to write it just as is. So here we go. We're going to say Mg solid. Hess's law is fun. Going to Mg2 plus has an enthalpy change equal to 461.96. There it is. I'm just rewriting it. Okay, good. Then we're going to say, okay, what about our other reaction? We look from the back of the book. We find that H2 forming 2H plus, our enthalpy change, our heat of formation for both are 0 from our direct method. So the change would be 0. So here we go. I do have to write it backwards though, because our H plus is on the reactant side. Here it's on the product side. And if we were to have a delta H of anything any other than 0, we would need to flip the sign and perhaps multiply by 2 if this wasn't the way it was written in the back. So here we go. Oh, no. Yeah, we're good. Okay. So I'm going to write 2H plus AQ going to H2 gas has an enthalpy change equal to 0. I forgot my negative sign. So the enthalpy change for the reaction, we need to add this up. Like I said, if we would have included the chlorine anywhere here, put it on the right side, you're going to see chlorine going to chlorine. It should be okay. So we now have the net, or the total reaction of MgS plus 2H plus AQ going to Mg2 plus AQ plus H2 gas. And our enthalpy change should just be the heat of formation for the magnesium. Here's the thing. This is what we expect per mole. Before you find your percent error, realize we didn't make a mole react. Okay? we did not let a mole of our magnesium go to Mg2+. This is where you have options. Do you have a question, Bear? What do you need, honey? Real quick. Oh, it's my folder. Thank you. Okay. We did not let a whole mole react. So there's various ways you can handle this. You could either do the unit conversion to say, oh, I didn't have a whole mole react. How can I figure out how many moles reacted? I'm going to give you an example here. So it says, determine your percent error. If this is the rate of heat that's liberated per mole and you use a different amount, take that into factor. And this should be easy. Anytime you see moles and you have grams, you need to do this. So let's just take as an example. Okay, if you were using your average, you could even find your average masses and do this. Or you can do it discretely all 3 times. But if you found out your average, let's go ahead and find your average mass and clean it up. So say you use 0.15 grams of magnesium the first time, 0.28 grams the second time, and thinking about this. Let's go ahead and just hopefully use the same amount every time. Let's just see, let me think about this, because I'm thinking if you use a different amount, you're going to change the temperature differently. So you would have to do it, if you didn't use the exact same amount every time, yeah, you would have to do 3 different calculations. So, yeah. So you're going to have to do this separate. So say you use 15 grams, real quick calculation though, you'll be all right. So grams of magnesium. Okay, so I'm going to find a molar mass of magnesium. I don't remember what it is. Good Lord.